Hello, everybody. Welcome back from lunch. I'm going to be helping out with this session today on visual comfort. And our first speaker today is going to be Qingyang Zheng, who's going to talk to us about his work and his colleagues' work entitled Recurrent Enhancement of Visual Comfort for Casual Stereoscopic Photography.
Hello everyone, this is Zheng Qingyang from Fuzhou University of China. I'm going to introduce our work, Recurrent Enhancement of Visual Comfort for Casual Stereoscopic Photography. In our work, the goal is to handle a challenging application, as shown in the figure. It aims to allow common users to create a stereoscopic photo using two images captured by a handheld monocular camera. This application has been named as casual stereoscopic photography. As shown in the figure on the left, users first take one image, move the camera horizontally and take the second image. However, the captured image pair can hardly satisfy the stereoscopic geometry constraint, let alone maintaining satisfactory composition and visual comfort. To solve this problem, existing methods often treat this as two separate problems, stereoscopic rectification and disparity adjustment. For stereoscopic rectification, they rectify two images by finding a pair of homographies, and then using them to transform the two images. The homographies are estimated utilizing either camera-calibrated parameters or epipolar geometry of the acquired images, as shown in the figure above. For disparity adjustment, there are mainly two types of methods for manipulating the disparity distribution of stereoscopic images. First, the disparity mapping methods adjust the disparity range of a scene by scaling it into the comfort zone via either depth image-based rendering or stereoscopic wrapping-based rendering methods. These solutions tend to introduce visually noticeable rendering artifacts when larger disparity change is performed. On the other hand, the disparity shifting methods improve the visual comfort by moving the zero disparity plane of the original scene. Its main advantages are low computational complexity due to its simple rendering process and no rendering artifacts in the processed images. The main contributions of our work as follows. To our best knowledge, our proposed framework is the first learning-based method to enhance the visual comfort of stereoscopic images in favor of the application of creating casual stereoscopic images. Besides, different from prior works, we present a recurrent deep learning-based framework to jointly and progressively handle the geometry constraint and the uncertain disparity range of casually captured images. In our life, we often iteratively adjust scenes and then evaluate our adjustment in order to progressively accomplish certain purpose. Inspired by such behavior pattern, we propose a unified reinforcement learning-based model. It mimics human behavior by recurrently manipulating the left and right views and then evaluating the visual comfort of the resulting stereoscopic image until it reaches the optimal condition, instead of trying to obtain the optimal stereoscopic images directly. Thus, we adopt a cost-to-find methodology. Particularly in the core stage, the state, including left and right images, disparity map, and historical action vector, is sent to the model for transforming images and then quickly evaluate its visual comfort. After that, in the final stage, we refine the disparity range of the previously processed stereoscopic images by shifting the left and right views to further enhance its visual comfort. From now, let me introduce our model's details stage by stage. In our formulation, the state is consisted of the input left and right views, the disparity of the views, and the historical experience. Especially, we use an LSTM latent layer, which encodes the historical experience by incorporating the previous actions. In this way, the state of the decision-making procedure not only considers the current observation but also involves the historical experience. The model learns the estimation for the optimal value of each action, defined as the expected sum of future rewards when taking that action and following the optimal policy thereafter. An optimal policy is easily derived from the optimal values by selecting the highest valued action in each state. In the course stage, we define a set of actions for the network to sample, which can transform the left and right views, including rotation transformations, perspective transformations, and a stopping trigger. The rotation transformation will rotate the left and right views by 1 or 2 degrees, clockwise or counterclockwise. We simulate the camera movements or the perspective transformation by using image wrapping. The image wrapping is determined by the displacement of image corners. According to different camera movements, coordinates of image corners are shifted on the horizontal and vertical axes, respectively. In the final stage, we define a set of actions for refining the disparity range. Without loss of generality, the actions allow us to fix the left view and horizontally shift the right view by multiple scales. Furthermore, the stopping trigger ends the recurrent process of our framework. During training in both stages, 2 identical deep neural networks are applied for the purpose of sampling the optimal action and determining the value of the policy, respectively. Their weights are denoted as theta and theta prime. After executing the action, we use a weighted sum of structural similarity index and VCA metric to measure the reward, so we can quantitatively evaluate the visual comfort of the produced stereoscopic image as the reward of the action. Then we use the mean square error as a loss function. For experiments, we randomly transform images from stereo image dataset to produce low-quality stereoscopic images as synthetic images. Based on these synthetic images, we evaluate our method in 2 separate tasks: geometric transformation and disparity shifting. In Table 1, we compare against image rectification methods, including a deep learning-based method. In Table 2, we compare with regression, exhaustive search, and disparity mapping methods. For all the results, our approach generally outperforms others in most metrics. Lastly, we collect a set of real-world images to evaluate our method. We build a dataset containing pairs of real-world images captured by monocular mobile cameras. Since they do not have ground truth for visual comfort evaluation, their quality can be assessed using a subjective user study. We ask 10 persons to compare the results of our method with those of the other 2 methods. The comparison stereoscopic images are displayed side by side on a 27-inch LED screen in a random order, while each user is mounted with an NVIDIA GeForce 3D vision glasses for viewing those images on a distance of 1 meter away from the screen. For each comparison, the users need to select the preferred image based on the subjective feelings. Especially, they need to answer the following 3 questions. For each participant, we calculate the times of selecting our results rather than those of comparison methods in the certified comparisons. On average, users prefer ours in more than 30 out of 35 cases when considering the image composition, visual comfort, or general visual quality. We also show the percentage of users selecting our results against others based on the general visual quality of the stereoscopic images for each image, which also implies that our method is superior to the others. On average, the percentage that users prefer ours over the combination of work 25 and regression is 88%. while the percentage that users prefer hours over the alliance of work 25 and mapping 26 is 92%. Here we show several examples of visual comfort comparisons on real images. As shown in second and third columns of the figure, the general rectification method focuses on reducing vertical disparity but neglects image composition. It also can be seen from the third column that the disparity mapping method inevitably introduces artifacts. Taken together, our method is more in line with the requirements of the application. Finally, we summarize our works as follows. In this paper, we propose a method to handle the application of casual stereoscopic photography. We utilize a unified reinforcement learning-based model to obtain the optimal stereoscopic images by iteratively adjusting the stereoscopic images and evaluating their qualities, which mimics human-like behavior in processing images. However, our framework still has several limitations. Training our model requires a large amount of data, and there is still a gap between the real data and our synthetic data. Besides, our approach currently relies on two-dimensional images without much consideration on three-dimensional applications. In the future, we would like to utilize the captured images from three-dimensional world to involve more three-dimensional information and thus to resolve more challenging cases. That's it. For more details, please refer to our paper. Thank you for watching.
All right, thank you for the talk. And we are now going to, we're going to have to skip questions because we're having some audio issues with the previous author. So I'd like to introduce the next speaker. It's Tobias Gunter, and his paper is Visualization and Evaluation of Ergonomic Visual Field Parameters in First-Person Virtual Environments. Go ahead.
And I'm a German researcher from the Technical University of Dresden. And today I want to talk to you about the visualization and evaluation of ergonomic visual field parameters in first-person virtual environments. So when you're designing a machine, like in machine engineering, you want to observe all ergonomic safety regulations. And so this might be an easy job for big companies. They have their own ergonomic experts, they have their expensive software tools, they have their digital human models, and they might even have motion capturing devices. But when you're in a small company, you have no dedicated experts. you have only your machine designers and your engineers. And for them, it's a really time-consuming job to look up all the norms and ergonomic standards. And also, small and medium-sized enterprises can't afford expensive software tools. And so we thought it would be a good idea to develop an easy tool for ergonomic evaluation. And the idea here is to create an VR assistance for engineers and machine designers so they can do a quick check for ergonomic parameters. And it also should be simple and quite cost efficient technical solution. So we thought it would be the best idea to use a commonly known VR system, the HTC Vive, with the controllers, as you all know. And we also decided to go for a little bit of tracking on the shoulders of the user. So we mounted the Vive trackers on the shoulders of the user with a backpack. So we think that's a really simple setup, and it's also really accessible for our target group of small and medium-sized enterprises. You maybe wonder why we choose VR in the first place. And this is because we want to have the immersive view. And it's also good for the native 3D content of the computer-aided design. Another benefit of this is that the evaluator, in our case, it's the machine designer or the engineer, that he feels the implications of his ergonomic decisions on his own body. And so we think this is a good thing to do. But for this, he has to imagine what it would be like to go around the machine, and he has to imagine what it's be like to be the later machine operator. So he goes around, he checks the working spaces, he checks his tasks, and he checks if the displays are all in the field of view. And so we want to help in this process. Our use case is only for visual field parameters for the ergonomic evaluation and not for postures and accessibility for now. And in our prototype, we want to analyze machine operation displays. You see it in the picture on the right. We have our sample machine with the display, and we also have a digital replica of this machine, which we used in the prototype. Here you can see an overview of the visual field parameters. We have the viewing angle, which refers to whether the user is looking straight away on the display or not. You have the distance, which is the space or the gap between the user and the display. You have the field of view, which refers to the side cone of the user. We also have a look at the height of the display and the chart on the pitch angles, which refers to whether the user is overstretching his head. So if he rotates his head too much. And for all of those parameters, you have to observe ergonomic limits. And we want to make it very easy for the engineers, and we want to show it to them in a really understandable way. And so we created some visualizations in VR. So here we have our semi-transparent spatial volumes, which are for the viewing angle and the distance. We have sectional disks for the field of view. We have a warning sign for the height, and we have blended textures, which are superimposed on the screen for the chart and the pitch angles. I will talk about the visualizations in the following slides in detail, and we will start with the spatial volumes. Again, remember, the goal for the evaluator is to go around the machine and to look if the displays he mounted on the machine are in a good position. And so you want to check our visualizations to get the ergonomic limits right. So he has to be inside of the volumes with his head. When you look at the picture, you see the green volume, and when he is inside this volume, he's inside the optimal ranges. When he's in the yellow volume with his head, he's only inside the narrowly met ergonomic limits. So it's okay, but not perfect. And in the red zone and outside of the red zone, he does not observe the ergonomic limits at all. So here's an example. First, we have a look at the distance on this little diagram. And we can see that user A is in the yellow zone for the distance. So it's just narrowly met ergonomic limits. And for person B, he's in the green zone. So his ergonomic limits are optimal. And for person C, he stands in the red zone. So he's too far away from the display. And so it's not sufficient anymore. We can do the same thing for the viewing angle. And let's have a look at user A again at first. So for user A, the angle is too steep to look at the display and it's not sufficient anymore. For user B, it's again in the optimal zone. And for user C, it's just in the yellow zone. This is only the viewing angle, but when you combine viewing angle and distance, user C is in the red zone overall because, again, for the distance, he is far away from the display. So both of the parameters have to be observed to get the right zone. So you maybe think, okay, it can be hard for the first person view to know whether you are inside of the volumes or not. And that's why we change the appearance of the volumes. So when the user is inside of the yellow volume, he just see the edges in this example here. So he's not seeing the faces of the volume, and he's also not seeing the red volume. So he knows, oh, I'm not in the red volume, I have to be in the yellow volume. And the green volume is shown like normally with the semi-transparent faces. So he knows, okay, I have to go a little bit to the right to be in an optimal position to check the evaluation, the ergonomic evaluation of the display, and to know if this is the right working space for the later machine operator. So here you can see a short video where you also notice how it looks like when the user is changing the displays, and then the visualization will appear there. For the sectional disks, the user has to check if his side cone will encapsulate the whole display. So in the picture above, you see the display is encapsulated by the green disk, and so everything is okay. In the picture on the bottom, it's only in the yellow zone. So here's a short video where you can see how it works. So if the user comes nearer, the display is not in the green zone anymore. Again, let's have a look at a small example. For person A here, the display is just in the yellow zone because the green side cone is not encapsulating the display as a whole. So let's now have a look at person B. Person B has the same side cone as person A, so the angles are the same for the ergonomic limits, but he's nearer, and so the display is not in the yellow zone anymore, it's in the red zone, and the ergonomic limits are not observed. This is a problem because person B would have to look a lot around with his head, with his eyes, and this is a much effort when you are at the workspace the whole day, and so it's not very ergonomic. For the height, it's of the display, it's very easy. The display can either be too low or too high, and when it's too low or too high, we show a warning sign. When it's not too low or too high, no warning sign will be shown. For the jar and the pitch angles, we will show a warning texture which is superimposed on the screen when the user is rotating his head too far. So when he's overstretching his head, he should not do the evaluation, and so he should be warned. In action, it looks like this. User is rotating his head and he gets the warning. When you do the ergonomic evaluation, you want to be sure that this works for all kinds of people and also work for small people and for big people. And so we decided to integrate a method where you can choose your body size and so check and also feel the implications of the ergonomic parameters on your own. And yeah, you can feel like a small or big person here. It can be quite confusing to show all of the visualization at once. And so we decided to integrate a menu option where you can turn them off and on. We also decided to integrate a fading mechanism. And this works like when the user is not moving much, then after some seconds, the visualization will turn off and it will reappear when the user is moving a lot. And so the site is not blocked. The user, when he's happy with the results, he can generate a report and show it here on the screen. And so he has all of the results. We did some feedback sessions with 2 ergonomic researchers, 1 machine designer, and some other researchers and students, and got valuable feedback for and some new ideas. For example, for the evaluation, the testers thought it would be a time-saving tool, and the conditions were really realistic. But they also liked to have some tutorial videos and to learn from other evaluators. For the visualization, they were really comprehensible and traceable, but testers like to have a barrier-free visualization. So we maybe should check our color scheme with red and green. It's not optimal. For the first person view, it was really immersive, but it can be also mentally challenging, and maybe an avatar as a reference point would help here. For the workflow, the users really like the interactive experience, but they use a little bit more of a guidance. So we should integrate tasks for machine operators so that the evaluators know what they have to do, and also maybe pattern of movements. Yeah. So the biggest concern with the prototype was the integration in a real company. For now, it's not possible because our processes are too manual. We do not have interfaces to the computer-aided design software, and also the transfer of the results and implications is not given at the moment. In conclusion, you can say that 3D machine models are really intuitively understandable in VR. And with our VR assistants, we have an interactive and immersive exploration opportunity for ergonomic parameters. And it's also very easy, and you don't have to use digital human models. The visualizations offer a great live feedback, but you have to be careful when you're combining them. For future directions, we would like to add specific workflows for evaluators, though that they have a little bit more of a guidance. And we also like to integrate computer-aided design content automatically. We want to do ergonomic evaluation of postures and accessibility. And we for sure want to do an empirical user study to validate our results. So thank you very much for your attention. And if you have any questions, you can ask them now.
Thank you, Tobias. We don't have any questions on Slido, but I do have a question to ask you.
Yes.
Okay. So did you consider or do you have any thoughts about incorporating near field haptics so that you can use the actual device when you're evaluating the ergonomics with the augmentation of virtual reality? So you could map in VR or even perhaps in augmented reality to be able to have the actual interaction with the device as part of the evaluation.
Thank you for the question. I think that's a great idea. We had no thought about it for now, because for the visual field ergonomic evaluation, you maybe don't need the haptics for now, but if you want to do accessibility, it would be a great addition, I think. So we also have to look how we do the tracking with this, because we want to keep the accessibility really low. So we want to use the Vive trackers for this, and we have to see if it's enough for this kind of evaluation.
Thank you. We still don't have any other questions. So if you have any questions for Tobias, please, he can probably hang out in the hub's room afterwards, and you can go and talk to him.
Okay, thank you.
Thank you. So now I'm going to introduce the next talk. It's going to be a video, but then questions can be asked. The talk is, the paper is called Virtual Big Heads, Analysis of Human Perception and Comfort of Head Scales in Social Virtual Reality. It's a conference paper, and the first author is Zubin Chaudhry, and he's going to be the speaker.
Hello everybody, my name is Zubin Chaudhry and I'm a PhD student at the Surreal Lab in the University of Central Florida, and I'll be speaking on Virtual Big Heads, Analysis of Human Perception and Comfort of Head Scales in Social Virtual Reality. So nowadays people interact each other socially either in real life or in social VR, and a very good example is how IEEE VR was in 2019 in Osaka compared to how IEEE VR is today. Most of you must be familiar with Mozilla Hubs, which is a social VR platform IEEE has used to hold the conference. So in these social interactions, nonverbal cues are extremely important. They exchange information where verbal cues don't generally do. So they could be facial expressions, gestures, body movement, and postures. And a very interesting experiment by Paul Ekman and Hager found out that over distance, the accuracy to read facial expressions reduces. And they found out that up to 45 meters, humans can still recognize some facial expressions. So we believe that the big head technique, where virtual avatars have a disproportionate head compared to the rest of their bodies, can be used to enhance the visibility of social cues over distance in VR. This technique has actually been used for quite some time. For example, it started off in video games as a mod. This is an example of a Nintendo 64 classic called GoldenEye, and nowadays we use it as AR emoticons. For example, Apple's Memoji app and Samsung's AR emoji app. So keeping all this in mind, we came up with the following research questions. What are the perceptual thresholds of head scales to recognize facial expressions? What are comfortable relative proportions of these head scales? And how do these changes have changes with respect to these distances? So we conducted the following experiment with 23 participants ranging from 18 years old to 31 years old, all from our university community. It was within subject design, and we used the HTC Vive Pro and the Vive controllers. The Vive controllers were used to adjust and select head scales. For example, you can choose a smaller head scale, you can increase the head size, or somewhere in between. So we used a life-size 3D female virtual human model as shown in the picture. She always had a standing idle animation, so it was a static environment, and she had 4 expressions always in a loop: happy, sad, angry, and skeptical. The VR environment was created to replicate our lab, so the participants were familiar with this VR environment as well as the physical environment. Our study design, we had 3 factors, so it was a 2 into 2 into 5 full factorial within subjects study. 3 factors being scaling methods, tasks, and distances. So our first factor is the scaling method, and we have 2: fixed neck height scaling and fixed eye height scaling. So for fixed neck height scaling, the heads increase and decrease in size from the neck, so it's always anchored around the neck. Whereas in fixed eye height, the virtual avatar's eyes are always maintained with the participant's eyes. So we do this by decreasing and increasing the body based on the head. So if the head increases, the body decreases, and if the head decreases, the body size increases. So this is done to maintain eye level at all times. So our second factor are our two tasks. The first one is the facial expression recognition task. We ask the participants to recognize happy expressions, sad expressions, angry expressions, and skeptical expressions on our virtual avatar's face. And the second task was to see the comfort levels of our participants for the different head scales they were choosing. So if they chose a head too small, then that would be too comfortable for them. So we wanted to know the thresholds of the comfortable proportions of the head scales. So our next factor are our 5 distances. We chose our 5 distances based on Edward Hall's proxemics theory, which states that there are 5 different spaces in a social interaction, being intimate space, personal space, social space, public space close, and public space far. So we chose our distances at these particular spaces. So our first distance is 0.4 meters in intimate space, 1 meter in personal space, 3 meters in social space, 6 meters in public space close, and 10 meters in public space far. This is how our participants saw the virtual avatars at the 5 different distances. So to our results, this is how our graph looks like. Our x-axis represents the distances of our virtual avatar, and the y-axis represents the head scale in log base 2. The two red lines represents the maximum head scale and the minimum head scale, and the green line in between represents the preferred head scale by our participants. The error bars indicate the standard error, and the green area in between the two red lines, the maximum and minimum, are the range between the two extremes. So our first result from our facial expression task was that we can notice an increasing graph for both head scales, for both head height scaling methods. So we can say that avatar head scales increased over distance. And another interesting finding was that so from 3 meters, so at 3 meters we can notice an increase from the zero value at y. So what that means is beyond 3 meters, participants had to increase the head scales to perceive facial expressions. So for humans in Paul Ekman's paper, we found out 45 meters was that limit, but in VR it is only a mere 3 meters. Our results from our comfort level tasks also is that it's an increasing graph, not as much as the facial expressions task, but it's still an increasing graph. So we can say that avatar head scales increase based on their comfortable proportions over distance. And also we can see that participants always increase the head scales at all distances, whether the virtual avatar was close or the virtual avatar was far. They always increased it as they preferred it over the regular head scale. So in preference of our scaling methods, the two scaling methods, we have fixed eye height and fixed neck height. Participants slightly preferred the fixed eye height over fixed neck height. This can be backed up by participant 18's comment, which was, I wanted to keep eye contact because it was more comfortable to me in this kind of situation. So in conclusion, I can say that up till 3 meters users can read facial expressions, whereas in real life, through Paul Ekman's paper, we can see that that limit is 45 meters. In VR, if we can use the big head technique, we can recover these lost cues, these lost facial expressions up to 10 meters, which is very, very impressive. And our second conclusion is that participants always preferred a larger head rather than a normal scaled head at all distances. As we can see, that big head technique has a lot of other possibilities, and we've thought of a few things we can do research in. Some of them are we can investigate the scaling of some other body part, not just the head, with respect to other non-verbal cues. not just facial expressions. For example, we can look into how gestures could play a role in having different sizes hands, because hands are extremely important in gestures. So we can try that. The next thing we can try out is having an adaptive scaling system. So we saw that at different distances there were different head scales selected by the participants. So over distance it's like a very dynamic range of head scales. What if a virtual avatar had always changed head scales based on the distance they were from somebody else? Would that be better than some other kind of system? We could look into that. The next research we could do is that how do these increased and decreased head scales affect social dynamics? Do people behave differently when another virtual avatar has an extremely large head or extremely small head? And we can also work with virtual avatars in more dynamics environments. As explained earlier, our virtual avatar was in a very static environment. She had a idle animation at all times. So social settings are generally more dynamic and it's more happening. So if we have a more dynamic setting or dynamic environment, heads the preferences of different people may change. So we could look into that. Thank you for listening to my talk. I hope you liked it. If you have any questions or suggestions, please email me at zubinchaudhry@knights.ucf.edu. And also, some of my lab mates are having a few more talks. If you're interested, please go and listen to them. Thank you.
Thank you, Zubin, for your talk. We do have a few questions in Slido.
Awesome.
Let me just Okay, so the first question is, do you think that using only one virtual human model and only one style in the study may reduce the generalizability of the results?
I completely agree with you. We did consider using multiple human models, multiple different styles, more cartoony, more realistic, but we decided to choose on this one. We do think that using different kinds of settings, like as I explained in my future work, it could be a dynamic setting, could be a static setting. The types of human models we use could affect our results. This model isn't the most generalizable, but it's just the starting step to what could affect VR environments with different head scales. But that's a very good suggestion.
Right. Yes. Thank you. We have a couple other questions that are related, which deals with the distance and how people were more comfortable increasing the head size and being able to notice the expressions. But to what extent do you think that relates to the resolution of the display, or perhaps the field of view, or text resolution, or whether there is something more related to the to more behavioral factors?
I think there's two answers to that question. The first being hardware related. Definitely resolution would play a role. As we get better resolution VR headsets, that limit from 3 meters would increase. That's what I believe. And also, it was limited to our headset. We did not try it on different headsets to see which resolution, what distances work with what resolutions and different hardwares. Also, the second reason could be, as you said, behavioral dependencies, like how people behave differently with different, like what their choices were. Many things could have affected that. So this 3 meters is restricted to our hardware and our participants. So it was an interesting finding, though.
Right. We have more time, and we do have more questions, so I'm going to continue asking.
Yes, go for it.
How acceptable would it be to increase the head size of someone else's avatar, which is what you did? Do you think this could be a sort of virtual glasses for your own avatar? And yeah, so what are your thoughts
about
in
this?
that area in terms of whether it's visible to others to change the head, or in a more social setting with more people?
That's actually very interesting, changing head scales of somebody else. Like if you could change it immediately, but we haven't thought about that. What we are doing currently is converting this VR setting into an AR setting, and to see how head scales, changing head scales work in AR. But but having it in a social setting is super interesting. I would love to know the answer to that, but I don't have it currently.
Okay, the last question.
Yes.
What do you think? Can these results be generalized to virtual agents rather than to human-like entities? So computer-controlled or robotic looking, or even like animal.
Yeah, that's interesting. I have another lab mate who works on AR animals, and we did discuss on having a big head on a dog, but it's still happening. Maybe currently, I think its best usage is in social VR, in virtual avatars, but this could definitely work in other virtual agents, as explained, as computer entities or robot-like, or in animals. We actually discussed about animals, and I would love to work on that too. Yeah, so that's what I think about it.
All right, Zubin, thank you very much.
Thank you for the great questions.
Thank you. All right, so our next talk is also a conference paper, as all talks in the session, and it's effects of dark mode graphics on visual acuity and fatigue with virtual reality head-mounted displays. The first author is Austin Erickson, also from University of Central Florida. And we are going to have a video presentation, then Austin is going to be available for questions. So please post your questions to Slido and take it away.
Hello everyone, I'm Austin Erickson. Today I'm going to be giving this talk about the effects of dark mode style user interfaces on virtual reality displays. So over the past 20 to 30 years, the majority of all our user interfaces on pretty much every digital device has been what's called light mode, or positive contrast style interfaces. So on these we typically have a light colored background, typically white, and then on top of that we put our dark colored text, typically black. And it's been around since the first what you see is what you get text editors from the late 70s and early 80s. But lately we're seeing this trend back towards dark mode or negative contrast style interfaces, where we have this dark or black colored background and then this white or light colored text put on top of that. So over the past couple years, all of the major operating systems companies have released operating systems with these type of settings for our users. So Apple, Microsoft, and Google have all released OS updates that allow our users to pick dark mode. So what's interesting is that we're seeing this trend for everything except for AR and VR devices. And we're unique with our VR and AR HMDs because the display sits 1.5 inches or 2 inches away from our eyes, whereas for all other display mediums, you're sitting further away from it. So the benefits and drawbacks to these type of UI styles may be different for HMDs in general than they are for traditional flat panel displays. So just by having that display so close to your eyes, it brings up 3 different factors. One of which is that the screen door effect may be visible on the display, although this is getting better with increases in resolution and with the display technology itself. It's still a factor at the moment. The other 2 things are that the screen luminance may cause visual fatigue, and it may even change our user's pupil diameter. So we have these things that are more of a factor to HMDs than they are for other types of displays. So how do these factors impact our standards for UI design? We actually ran one study on this already, investigating optical see-through AR HMDs. For that we used the Microsoft HoloLens, and they have this other unique problem that since it is an additive light display, they can't render black text, just black at all. It just shows up as transparent. So when we ran a study comparing dark mode and light mode interfaces, we saw that dark mode both improved our users' visual acuity significantly, and it significantly reduced the amount of visual fatigue compared to light mode interfaces. So for this, we wanted to measure these same things on VR HMDs to see if we still had similar benefits there. So I mentioned earlier there were 3 factors we were considering, one of which is the screen door effect. So as you can see at the top here, if we use a dark mode interface, the screen door is kind of masked by that dark background, but then it has the drawback of appearing more prominently over the text that we're trying to read. And then the opposite happens if we use light mode. It's more prominent across the entire interface in general, but then it's less apparent on the text itself. We also have these factors of visual fatigue and pupil diameter. So with the dark mode style interface, you're typically introducing less light to the user's eyes, which will result in less visual fatigue and a more dilated pupil. Whereas if you have that light mode interface, you have more light reaching the eye, which typically results in more visual fatigue, a constricted pupil, and may have this interesting effect called the pinhole effect if the pupil size is reduced enough. That pinhole effect can cause an increase in acuity, as well as some other interesting effects here. So in some prior work by Jones et al., they investigated perimeter lighting or peripheral lighting, where they had a ring of LEDs around the inside of a VR head-mounted display. And they found that when these LEDs were turned on, that their users were actually better at estimating distances between objects. So they had improved distance estimation with this light turned on, a really easy thing to do. Again, those lights constrict our users' pupils, and it's also a known effect that this can cause an increase in visual acuity. So a very simple thing to try if we're looking to squeeze the most acuity for our users. We designed a study based on these 3 factors. So we have a 2x2x2 full factorial within subjects design, ended up with 18 participants. Our 3 independent variables were the color mode, which could be either dark mode or light mode. Then we have our virtual lighting, which as this study is taking place in virtual reality, we have a virtual environment that houses our user interface. It's either very well lit in a bright virtual environment, or it is a dimly lit virtual environment. Our 3rd variable is perimeter lighting. So instead of introducing a ring of LEDs like Jones et al. Did in their work, we decided to illuminate the outermost pixels on the display. So the pixels on the top, bottom, left, and right are turned to white for so many rows in, just to add more light on the display with the attempt to constrict our users' pupils a bit. We did have three dependent variables, which were the visual acuity of our users. We measured this using a Landolt-C acuity chart. It's a very common type of visual acuity chart. Instead of having a bunch of different letters, it's all the letter C. It's just rotated in 90-degree increments. So our users just have to tell us which side of the C has the opening. So they'll read it as up, down, left, or right instead of A, B, C, or D. We're also looking into visual fatigue. To measure this, we use a survey called the Convergence Insufficiency Symptom Survey. We give them this after each of our conditions to get a rough estimate of how their eyes are feeling. And this is a pretty commonly used survey for these types of things as well. Our third measure is a usability score. So we use the user experience questionnaire short version after each of our conditions to get an idea of how easy it is to read text on these user interfaces under these various conditions. So our study environment looked like this. Our participants came in, they were seated in an isolation booth at a desk, and then they would be asked to put on the HMD, which in this case was an Oculus Rift S. From there they would read paragraphs that were floating out in front of them for 1 minute to themselves. There's 4 paragraphs, so they go ahead and read those in their head to get an idea on how easy it is to read under these lighting conditions. After that, those paragraphs disappear and are replaced with an acuity chart that we discussed earlier. From there, our participants read as far down that chart as they possibly can, all the way down to the bottom if they can. They take off the HMD after that. They do those 2 questionnaires we mentioned, and we repeat for every condition. So our conditions looked somewhat like this. On the top row we have our bright virtual environment, and on the bottom row we have our dimly lit virtual environment, and then we have the paragraphs on the left side of the screen, our acuity chart on the right. The important thing to notice here is that the colors are the same between light mode and dark mode changes. So if we look at the top row at our bright virtual environment, we're using white pixels and black pixels, regardless of which mode is being used. However, when we change the environment to be the dimly lit virtual environment, the contrast level is reduced. Instead of white pixels, they go to a gray color. So we have gray and black pixels. And again, those are the same colors for both light mode and dark mode. So here's our first page of results. These are all our visual acuity results. Here we see that we had on the left side the number of errors made by participants broken down by condition. So on this chart on the left, higher is worse. We want these scores to be low. So we did see a significant effect of our virtual lighting on the number of errors, and that's to be expected. So if we compare the left side of that first chart to the right side, we see that when we're in the bright conditions, we have lower errors, so they're making less errors. And then when we move over to the right side and we dim the lights, they make more errors. And again, we believe that's due to that decrease in contrast that happens just with the coloration of the user interface. We can then break these down by pairs. So if we look at the bright virtual environment on the far left with no perimeter lighting, we see that light mode, our users in light mode made less mistakes than they did in dark mode. So, and this was a significant difference. When we turn the perimeter lighting on and we go over a column, we see that we lose that significant difference. And then as we continue over without perimeter lighting in a dim virtual environment, we see that users actually made less mistakes with the dark mode interface than they did with the light mode, and this was a significant difference. And then again, we lose that when we turn the perimeter lighting back on. So it's interesting that we're seeing these opposite effects depending on the virtual lighting in the room. On the far right side of this slide, we also have a measure that is the maximum row number achieved by our participants without making any mistakes. So on this chart, higher is better. You want them to read all 7 rows without making any mistakes if they can. So we actually see similar results. We did have that significant main effect of the lighting, so that people were able to read further down on the chart in the bright conditions than they are in the dim conditions. We did, however, lose our significant result under the brightly lit environment for no perimeter lighting, and we only see that significant difference in the dimly lit environment between the light mode and dark mode interfaces without perimeter lighting turned on. We also have these measures of visual fatigue, and these were more straightforward. What we found is that color mode does have a significant effect on visual fatigue scores. So when we look at this chart, you want these scores to be less. Less means less eye strain, whereas more means more eye strain. So when we compare our light mode and dark mode columns here, we see that across the board, dark mode does tend to have lower visual fatigue scores. And then there were significant differences for both conditions in which the perimeter lighting was turned off. So to summarize those results, for dark mode or negative contrast user interfaces, we found that our users had better visual acuity in dim virtual environments. They actually had reduced acuity in bright virtual environments, and in general, they had reduced visual fatigue overall. On the other hand, with light mode or positive contrast user interfaces, our users experienced reduced visual acuity in dimly lit virtual environments. They had better visual acuity in bright virtual environments, and they had increased visual fatigue overall. So from this, we have some recommendations for just work in VR in general and user interfaces. And they are to go ahead and use that dark mode if you're using dimly lit virtual environments. You go ahead and switch it to light mode if you're using primarily bright virtual environments. And then if visual fatigue is a concern, or if users are complaining of visual fatigue, switching to dark mode may be a really easy fix. So thank you guys so much for your attention, and I will be around in the chat here to answer any questions that you may have. Thank you.
Thank you, Austin, for the great talk. While we wait for questions to pop up on Slido, I do have a few questions. You touched at this at the end with recommendations, but virtual reality typically involves 3D immersive environments and not just reading off a screen of text, right? So I just want to hear your thoughts on, you did mention guidelines, but how, in what kind of applications? Would that be billboards and signs on virtual environments, or would it be more when there's more larger amounts of text? What are your thoughts about that?
That's a great question. This study, we were in general concerned with those small text sizes. We're having people read those acuity charts, and we're getting way down to the smallest letters that we can realistically display on these devices. So as far as practical applications go, there's probably not very many where we are going to be displaying text at that size. So one of the things we do want to do in the future is do another study investigating text at more practical sizes to make these kind of comparisons. And I think we could come up with some nice guidelines from the results of that.
Right, yes. And also, just to follow up on that, you didn't account for the luminance of the environment itself, but only, as I understand, but only of the panels. Is that right? So was it a dark, like was the text always over on top of a dark background, or did you vary that?
I am not 100% sure I'm following you on this one.
Okay, so what I'm saying is you had a black, correct me if I'm wrong, but did you have a black virtual environment with text panels that were either lit or not lit? And that may be answered also by the VR luminance, but did you have did you vary the brightness of the environment itself, or just of the?
Yeah, okay, I see what you're saying. Yes, we did. So we designed a very plain virtual room. It was just a cube that had kind of beige colored walls in Unity. And then we did adjust the virtual lighting in that room. So there is a change in kind of the coloration around that Acuity chart as well.
Okay, yeah, that answers that. Thank you. Another thing that I wonder is whether you looked at, I'm sure that there have been a lot of studies on the effects of brightness on screen reading, and whether the results that you found for VR, does that replicate and match what is known in regular desktop reading, whether it's in dark or bright mode?
So I don't recall reading any comparative studies between dark mode and light mode on traditional displays. I would definitely have to do some looking to get a firm answer for you there.
Yeah, it would be interesting to understand whether, I mean, we know that just anecdotally, we all feel less strain when you're in dark mode,
yeah.
But you also have other environmental factors in the real world that can be different than those in virtual environments.
Absolutely.
Yeah, we do have a couple questions that are coming in here. So, and we do have plenty of time because we didn't have questions for one of the speakers who wasn't able to be here. So, I'm sorry, who had audio issues. Did you consider participants with glasses, either myopia or hyperopia? And if so, was there any difference?
So we did have participants in the study who wore glasses, but we did not analyze our results in terms of who did and who didn't. That would definitely be an interesting thing to look into to see if that has an effect on either the Acuity scores or the eye fatigue scores.
Right. Another question is, have you thought of populating the environment with objects and then add the text on a UI and play with the UI mode and lighting mode, I guess, to do more of an interactive control?
That would be interesting. Yeah, that's not something that we'd considered. Most of what we have so far has very unpopulated rooms. It's just kind of an empty cube that you're sitting in. Maybe in some of our future work, that's something that we can investigate. We did do a similar study in AR where we did take the background of the environment into consideration. We had like 3 different backdrop posters that we used. So we did investigate it there, but we haven't done anything similar for VR.
Thank you. Final question for this talk. Have you measured the luminance of the VR display? And they're curious to see what the difference is between the HMD and AR studies and a typical display and how it may inform the effect of dark mode. I think that also relates to my question on comparing to other studies.
So we currently don't have the tool to do this, but it's definitely something that we want to do. Obviously our results from this particular study, they can't necessarily be generalized across all other HMDs because of those variations in luminance. So we do want to get some measurements there and kind of compare those measurements between the head-mounted displays and see if that would have significant effects between the different head mounts.
All right. Well, thank you very much for the talk. And now we're going to transition to the next talk, which is going to be a video again.
Oh, okay. Thank you so much.
Our last paper in the session is also a conference paper, and the title is Exploring the Differences of Visual Discomfort Caused by Long-Term Immersion Between Virtual Environments and Physical Environments. The presenter is going to be Diego.
Hello, everyone. My name is Jie Guo from Beijing Institute of Technology. Now, I will introduce our work. The title of our work is Exploring the Difference of VR Discomfort Caused by Runtime Immersion Between Virtual Environments and Physical Environments. Our work includes 5 parts: Introduction, Materials, Experiments, Results, and Conclusion. The first part is Introduction. As we know, with the rapid development of computer technology, HMDs are becoming more and more popular. People use it for entertainment, education, training, and other fields. And with the performance optimization of HMD, the use time is becoming longer and longer. If people use HMDs for playing games, it will take more than 30 minutes. If they use it for studying, it will take 60 minutes. And if they use it for watching a movie, it will take for more than 3 hours. So it is a tendency that HMDs will be longer and longer used. But before the long-term immersion, it is necessary to explore the effects. As a common symptom of discipline, VR fatigue needs to be considered. There are so many studies have explored the VR fatigue in HMDs, includes the inducement, such as the disparate blue illumination and the divergence accommodation conflict. There are also some studies have explored the difference between HMDs and other disciplines, such as the vergence distance and the accommodation distance, the FOV and the focal distance. They also have explored the difference between HMDs and the 2D disciplines, the difference between HMDs and the 3D disciplines. But most of these studies are based on short-time immersion. Of course, there are some studies have explored the long-time immersion in VES. Stanek and Broad conducted a 24-hour safe experiment in a fully isolated virtual world, and 1 male participant took part in the experiment. After that, Rodell conducted a 12-hour experiment to explore the effects of long-time immersion in virtual environments. But these studies are based on small participants. So, it is necessary to conduct a scientific research to explore the VR fatigue in long-time immersion in virtual environments. In this paper, we designed 8 hours comparative experiment to investigate the VR fatigue caused by long-time immersion in virtual environments and compare the result of the physical environment. The core contributions of our work can be summarized as: firstly, we explore the changing of VR fatigue in virtual environment at a adult work rhythm, and we compared the difference of VR fatigue between virtual environments and the physical environments, and explored the influence of different factors in two environments. Thirdly, we investigated the correlation between the subjective VR discomfort and the objective augmenter indicators. The second part is material. The first is apparatus. The computer we used in this experiment is shown in this. The HMD we used in this experiment is HTC Vive Pro. The more details about these HMDs is shown in this. The entry experiment was carried out in the same space to avoid the different illuminations. The experiment space is shown in figure A, and the whole experiment was happened in a closed space to avoid the effects of sunlight. Figure B shows the physical environment, and the chair in this experiment is fixed, and the distance between the discipline and the subject as is 16.5 centimeters. Figure 3 shows the virtual environment. The virtual environment was a realistic style virtual office environment, and the people can do some computer work in this environment. The brightness of HMDs and the physical environment was matched by the illuminators. There are two types of vision stimuli. The first is the text task, and the second is the text image mixing task. Each type of vision stimuli have two intensity, including the high density and the low density. The first is the document collection task. It is a high-density test task. The low-density test task is the textile input task. The third is a high-density mixing task, which is a keyword searching task. The fourth is a low-density mixing task. It was the image classification task. The third part is experiments. The first is the participants. We adopted a vision subject method to design the experiment. 13 volunteers took part in the experiment, but 3 of them gave up the experiment when they first did the task in the physical environments. Finally, there are 27 participants finished the experiment. The mean age of the participant is 24 years old, and in their daily life, they spend a mean time of 7 hours in watching different displays. The more details about the participants is shown in the table. The whole experiment procedure contains 3 parts, including the training test, the virtual environment test, and the physical environment test. The virtual environment test and the physical environment test last 8 hours, and the participants in virtual environments need to wear HMDs continuous during the whole experiment except the launch. All participants finished the task in the virtual environment condition and the physical environment condition. The order of the VR condition and the physical condition are randomly decided. The virtual environment conditions and the physical condition task were performed on different days, and the participants need to finish another test after a week's recovery. On the day before the participants' first test, they were treated to familiarize the work experiment contents. The training contents including the experiment contents training, and after the contents training, they were asked to experience a VR game for 30 minutes. It is aimed to exclude those participants who had a major discomfort of VR. And according to the vision stimulus, the test phases including 4 tasks, and each stage lasts 16 minutes, 90 minutes, including 60 minutes task, 20 minutes subjective measurements, and 20 minutes rest. The picture shows the details of the experiment, and if the more details about the experiment procedure are shown in our paper. We use subjective measurements and objective measurements to evaluate VM fatigue. The subjective measurement is the VM fatigue scale. VM fatigue scale includes 24 items, and each item has 7 levels. It can test 5 symptoms about VM fatigue: airstrain, general discomfort, nausea, focus difficulty, and headache. The objective measurements including the pupil size and the accommodation response. The pupil size and the accommodation response are tested by the refractor. The first part is results. The results of the subjective measures. Results of the airstrain. This figure shows the results of the airstrain. The results of the airstrain shows that the mean score of airstrain is statistically significant with the factor of time and the environments. It means the symptoms of airstrain are becoming significant several after the VM tasks, and the symptoms of airstrain can be alleviated after runtime rest. The result also shows that, except the first task, the changing score of the symptom airstrain in the two conditions have no significant difference. It means that the airstrain in the first task is the most severe between the two groups. The result of the focus difficulty is similar to the airstrain in the point of A, B, C, but it is different of D. The participants have more severe symptoms of focus difficulty in virtual environment conditions after 1 day work. The result of nausea shows that the symptoms of nausea are statistically significant with the factor of environment, where there is no significant difference with time. It means that the VR condition and the physical condition have induced later symptoms of nausea. The result of the headache, the general discomfort, and the VM fatigue scales is similar to airstrain. The results of pupil size show that the pupil size is a significant difference with time, and there is no significant difference with environments. The result of the accommodation response shows that the relative accommodation response and the maximum accommodation response are significantly changing with time, while the minimum accommodation are changing later. Conclusions. There are also some limitations of our study. The first is the VM contents in virtual environments are still 2D, which is different from the daily use of HMDs. And the pixels in every unit between the two disciplines are different. That may influence the result. And the third is the age of the participant is too concerned, which limits the universality of this result. In this paper, we have explored the effects of VM discomfort in virtual environments, a daily organism, and compared the results with the physical environments. 27 participants subjected VM discomfort and their objective VM fatigue are tested. The results show that the subjective VR fatigue symptoms, the objective pupil size, and the relative accommodation response are changing with time. The pupil size is negatively related to objective VR fatigue, and the long-term work based on discipline only influences the maximum accommodation response of participants. Thank you very much.
All right, thank you for the talk. Unfortunately, the author had a technical problem and wasn't able to join. So we do have a few questions that I encourage whoever has questions to reach out to them by email. For everybody else, I encourage the authors and also the audience to hang out at the hubs rooms so that you can ask specific questions during the break. Thank you.